Stanford University.
Lecture 7 of Stanford CS 193P Spring of 2021 is all about animation. We're going to find out how that works. Along the way, we're going to have to learn about view modifiers because they're very much involved in animation. But let's dive right in, talk about animation. It's very important in a mobile UI, so Swift makes it very easy to do. Now, one way to do animation is by animating a shape. That's how we're going to make our little pie on the back of our cards in Memorize kind of look like it's a countdown timer by having its angles animating there. But the other way to do animation, far more common, is to use view modifiers. So in all animation that you see that's not happening with shapes is happening because some view modifier somewhere is animating something. So what is a view modifier? Well, you know all those little functions that modified our views like aspect ratio and padding and foreground color and font and all those. Those are likely turning right around and calling a function in view called modifier. For example, aspect ratio is likely something like dot modifier, aspect modifier, or aspect ratio modifier, or something like that of 2/3. And this pink aspect modifier, or whatever it's called, can be anything that conforms to the view modifier protocol. So let's take a look at this view modifier protocol. It only has one function in it. This function's only job is to create a view using some other view. In other words, modifying it. So it looks like this. It's got this func body content. The content there in purple is actually the view you're modifying. So if I call dot modifier on some view with a view modifier as its argument, then I am going to have this body content right here called with that view I'm modifying as the argument. Now, the code in a view modifier, you're going to see, looks a lot like code in a view, and that's because view modifiers are views. The only thing that's really different about them is they're being passed some other view that they're going to use when they build their own body. So writing the code for a view modifier is almost identical to writing a code for a view. It can have @state and all that stuff. And just so you're aware, there's also a special view modifier called geometry effect. It's good for building view modifiers that only modify geometry, like scaling, rotation, or translating. I'm not really going to talk about geometry effect. Just want to know it exists if you happen to one day want to build a view modifier that's only a geometry view modifier. But we're going to focus on view modifiers in general and how we implement that protocol above. This is probably best learned by taking a look at an example of it. So we'll use Memorize, of course, as our example. Let's say we wanted to create a view modifier that would cardify another view. In other words, we would take that other view and put it on a card, like in our Memorize game. And it would work with any view, not just our text with some vehicle or ghost here on it. What would it look like to write code to make a Cardify modifier? Well, the first line you see at the top there is what it would look like to use the modifier. So I have my ghost text. I'm calling dot modifier on it with my new view modifier that I'm writing called Cardify. I even got an argument there, is face up is true. And we're going to actually go do this in Memorize in a minute here. So in the slides, I just want to highlight a few things about the way this works. The first one is that content argument to the body func instead of body var in view modifier is just that text ghost. And not only is it passed to us in the body, well, of course, we're using it in the body. In this case, we're using it in the front part of our card, right? The is face up part of our card. So that is all that argument is there. The second thing is to notice that this modifier can have arguments. Ours has is face up as the argument, and we're just using is face up as we normally would inside that Z stack to pick the front of our card. But we provide those arguments the exact same way as a view. I just have a var called is face up. I could have an init with argument is face up. That's allowed too, just passing these arguments in. And these arguments are crucial in view modifiers because these arguments are the things that when they change, kick off animations. And we're going to learn all about that in the next lecture. but I just want to make sure you understand that arguments to view modifiers are crucial. And finally, when you do dot modifier, it is returning a view, some view. You see it says body content return some view. In this case, I'm returning this purple Z stack thing. That is what's returned. And I've been telling you all quarter that these modifiers like border and color and font and padding, they are just taking some view and modifying it and returning a new view. And now you can see them doing exactly that with this body content right here. Now, I've been saying dot modifier Cardify is face up true, but of course all of our other modifiers that we use would just say text Cardify is face up. So how do we get from the top line there to the bottom line? So easy. We already know how to do this. I'm going to add extension to view that's called Cardify is face up, and its implementation is just going to be return self.modifier with a Cardify. And remember that self in there is the view because this is an extension on view. I'm adding this function to view. So it's simple as that. We'll do that in a demo as well. So let's dive right into that demo and show how all this stuff is done. Okay, we have spent the first 3 weeks of this course using a lot of these little view modifiers, opacity, foreground color, and padding. And what we're going to learn in this demo is how to create our own view modifier. Now our view modifier is going to be very similar to padding, right? Padding takes any old view you want, add some space around it, some padding around it. Well, our view modifier is going to take any old view you want, and it's going to turn it into one of these cards. When the card is face up, you're going to see whatever the any old view you're modifying is. When the card's face down, it's just going to be a filled-in rounded rectangle like this. So let's just dive right into creating our first view modifier. We're up here to File, New File. Now, view modifiers are SwiftUI views, but just like shapes, which are also SwiftUI views, we do not use this template down here. This template down here is when you're making a basic view that has a var body, and you're going to see that view modifier, it has a body, but it's not exactly the same as your basic view. So we're going to do Swift file here. I'm going to call my view modifier Cardify, because that's essentially what it does. It takes any old view and it cardifies it. Essentially wraps a card around it. Let's make sure it's in the right place, right group. Here we go, cardify.swift. Now, view modifiers are most exceptionally UI things, so we're going to say Swift UI as our import. And creating a view modifier looks a lot like creating a view. It's just ever so slightly different. It's a struct. We'll call it Cardify. It's a view modifier instead of just a view. And instead of having var body that is some view, it almost has that. It has a func called body that has this content argument right here. This content is what we're modifying. So when we use this modifier, this is the view we're modifying. And all we're required to do is create a body very similar to when we did var body, some bunch of UI building code in here that is the view we want to return from the modifier. So now hopefully you're really seeing what I'm talking about when I say that these modifiers, they take some arguments and then they return a view. And that's exactly what's happening here. This is the view that the modifier returns. So our body is supposed to look like a card. Now let's just go back over here and grab the code we already have that draws a card. Copy and paste this whole thing into here. Now, of course, we can't reference cards in here or anything like that. This has nothing to do with cards. So for example, card is matched, this whole thing, just get rid of that. We're not doing anything with emoji memory game cards. We're just cardifying any old kind of view here. This pie and text is, for example, what we cardify in our emoji memory game. So that gets taken out and instead is replaced with the content, right? The view that we're modifying here is what we're going to put inside of our car, not the pie and the text, but whatever we're modifying. And we have no emoji memory game card here to do is face up, so we're going to still need face up because our cardification wants to still be able to do face up. We're going to have to add a var up here is face up, which is a bool, where whatever view we're cardifying, they're going to have to specify when they use this modifier whether they want the card to be face up or face down. Now we've got these drawing constants. We'll have to bring those over as well. Here they are. Copy, paste. Don't need the font scale over here. And in fact, back here, we now no longer need the corner radius and line width because the cardifier is going to do all that for us. We'll build over here. No errors over here. So we have built a view modifier. It's a simple view modifier that just takes whether you want it face up and returns back a view, which is something that looks like our card. Now you see what I mean when I say creating a view modifier feels a lot like creating a view. And in fact, this is a view. You can do things like @state and other stuff in here. The code in a view modifier looks very much like a view, and all the things you've learned about creating views, they pretty much apply to doing view modifiers as well. The only special thing about them is that they're modifying some other content, and so you're getting this, which you include usually somewhere in what you're building. Now, how do we use this view modifier? How do we use it back here to get rid of all this extra code? Well, what are we modifying? What are we putting on the card? It's this pi and this text, these stacked on top of each other. That is what we want to be cardified. So let's take out all the code except for that z stack of those two things. And then let's cardify that. So how do we call that cardify modifier? You can call any modifier in Swift by doing .modifier and just creating one of those view modifiers. Now ours requires us to provide this is face up, which is just our cards is face up here, so that's no problem. And if we build this, no errors. That is it, just simple as that. Let's make sure it's working over here, resume. There it is. We can even go into live preview mode here, click on some cards. It's still working just exactly like it used to. Let's convince ourselves that we can cardify any view by commenting that out and just cardifying a circle. There it is, look, cardified circle. Maybe we put some padding on the circle. Could even put some opacity, 0.3. Any view can go here, and our modifier, Cardify, can modify it, put it into a card. So this is really nice, except when we use other modifiers like padding and opacity, we're not having to say .modifier padding 5 or .modifier opacity 5 or something, or 0.5. We just get to say opacity, and we'd really like here to be able to just say .cardify. This would be a lot nicer looking code. Well, where does this function come from, this cardify? This has got to be a function on view, and so somewhere we have to define this. And we almost always, when we create a view modifier, create a little extension to the view protocol that defines a function that is the function we want people to call to cause our view modifier to modify it. So I'm going to say cardify is face up, takes a bool, returns some view, as all view modifiers do. Here I'm just going to return myself.modifier, cardify is face up, is the is face up view passed. So I'm doing the same modifier cardify, I'm doing it on myself, and since this is an extension to view, then this works on self. Don't need the return, it's a one-liner that clearly returns some view. So now that I've defined this cardifier is face up, I'm going to go over here, build. It works, perfectly valid to say this, and we can resume. start clicking on our cards. They're working just fine. We're going to talk about animation in a few moments. And when we do, you're going to find out that animation really only happens two ways. Shapes, they can be animated, and we're going to animate our little pie shape, and view modifiers. View modifiers can be animated, and so turning something into a view modifier, especially something like this card, is really valuable when it comes later to doing custom animation, which we need for a card. Because when we click on a card, we want it to rotate and flip over, kind of a 3D rotation to flip our card over. And that animation code is going to happen inside this view modifier because all custom animation goes on inside view modifiers or shapes. So let's get back to the slides, talk about animation, and then we'll come back in here and we'll animate this and we'll animate this and we'll do a whole bunch of other animation here while we're at it. Now, before we dive into the mechanics of animation and really understanding how to make animation happen on screen, let's talk about some of the basic principles, the golden rules of animation. First thing to understand is that only changes can be animated. If nothing has changed, then there's nothing to animate. That's a fundamental rule. And what sort of changes can be animated? Really only three kinds. Arguments to view modifiers, shapes, which is the arguments to the creations of shapes, and the existence or not of a view in the UI. So the comings and goings of views. That's it. That's the only things that can be animated in Swift UI. Another thing to understand, basic understanding, is that animation is showing the user changes that have already happened. Your code is not running as the animation is happening. Your code does something, makes some change to these things mentioned above right there, and then the animation system shows that over time to the user, but the change has already been made in your code. Your code has moved on from there. And this takes a little bit of adjustment, but once you understand this, it actually makes writing animation code and making it work make a lot more sense. That your code is just running and making changes, and that the animation system is taking care of showing that to the user over time. Now, view modifiers are the primary change agents in the UI, of course, but you have to be careful because a change to a view modifier's arguments has to happen after the view initially gets put in the UI. In other words, the changes to the view modifier's arguments are the changes since it joined the UI. Another thing to understand is not all view modifier arguments are animatable. For example, .font. Its arguments are not animatable. We're going to see that in the demo. We're actually going to work around that and choose a different view modifier to do our scaling of the font that is animatable. But most view modifiers that you would expect to be animatable are. So even things like colors and things like that can be modified. Now, when it comes to this coming and going of views on screen, that similar kind of restriction there that it's only going to work if that view is coming or going into or out of another container view that is already in the UI. So if a view comes on screen with its container, then it's the container that would have to be animated, not the view that's inside the container. We'll see a little bit later how we can find out that my container came on screen and then do something to cause me to come on screen if I want to animate myself on separately. You might be thinking, how is it that views come and go on screen? Well, mostly it's if-elses in view builders. That's a common way that it's happening, but also for eaches, right? A for each has got an array and things change in the array, and that makes views get included or not included in there. This is generally, at least the ways you've seen, that views can come and go. All right, so we know that it's changes that we're trying to animate. How do we make these animations happen? Well, there's three ways. One is implicitly, that is automatically, by using a special view modifier called .animation, which takes an animation as an argument. So we'll talk about that. Second is explicitly. This is a case where you are going to do something that's going to cause a lot of changes, and you want the entire UI to coordinate the animation of those changes. And that's done with this simple Swift function called withAnimation. It also takes an animation. We'll talk about that again in a second. And then a little block of code. And whatever you do in that block of code is going to cause a bunch of changes. Maybe it's a user intent function, changing something in your model. And that's going to cause your UI to have a whole bunch of view modifiers have their arguments change. And that whole thing is going to be animated using whatever animation description you provide in that little animation argument there. And lastly, making views be included or excluded from the UI can be independently animated as well, although a lot of times that is animated with explicit animation. Now, all of these are only going to go if they're happening in views that are already part of the UI. I'm probably going to say this 5 different times because when students go off to write their animation code and they're like, oh, my animation just doesn't work. I'm writing the code right. And the answer is that there are things that are changing that they're expecting to be animated are happening to views that either aren't on screen yet, or the change happens as the view comes on screen. And so it's not going to get animated then. It has to already be on screen. All right, let's talk about this implicit animation. This is sometimes called automatic animation. You essentially mark a view so that all the view modifier arguments that precede the animation view modifier will always be animated. And these changes are animated with whatever duration and curve that you specify. We'll talk about what that means on the next slide. Here's a little piece of code that uses this .animation view modifier. I've got a text there, a ghost. Maybe it's the text on a card that's playing Halloween theme or something. And I've got 2 view modifiers there. Opacity, you're familiar with that one. Notice the argument of opacity is a ternary operator. Hopefully you know what that is, maybe from other languages. It's a simple little operator that has a bool, in this case called scary, and then a question mark, and then 1 if scary is true, and 0 if scary is false. All right, so the opacity modifier there is going to change the opacity of the text, and depending on what scary is, that's going to say what the opacity should be. And similarly, we have another view modifier, rotation effect. It's got an angle there, and the angle is either 180 or 0, depending on some Boolean var upside down. So scary and upside down are vars. They might change for some reason. Maybe something's coming out of the model or whatever. They're changeable. And by putting .animation, animation ease in, out, which we'll talk about what ease in, out means in a minute, that makes it so that anytime scary or upside down change, those changes will be animated, right? The opacity will fade from one to the other. The rotation will actually show you the view rotating around to upside down. It'll be sideways halfway through. And that's going to happen all the time, just by putting this animation on there. Now, one thing that's important to note is that if I put more view modifiers on this view after the animation, they will not be animated. So the animation view modifier there only causes the other view modifiers that are before it on that view to get automatically animated. And if I left that .animation view modifier off, then changes to scary and upside down would happen instantly on screen. The text would go from completely transparent to completely opaque instantly, or from upside down to right side up instantly. So that's what this .animation modifier does. It just causes other view modifiers above it, that the ones that are animatable anyway, to animate their changes. Very important to understand, this animation modifier does not work very well with containers. And we usually don't use it on containers. That's because containers propagate the .animate into the views inside the container. So in that way, it's a lot more like font or foreground color, not like padding. When you say animation on a container, you're not saying animate the container, you're saying, I want this animation to happen to all of the things inside, which can be it can make for unexpected results unless you really understand what that means. And you might even want to go and put the animation on all of them separately, just so you're sure you understand which other view modifiers you're causing to automatically animate. Now, the argument to that animation view modifier is an animation struct. And this animation struct is just a bunch of parameters that control how the animation works. For example, you can control its duration. There's a var for that. There, you can control its delay. You have to call a little function on the animation struct to change its delay, but you can do that. You can decide whether the animation repeats. Maybe it repeats a certain number of times, or it can even repeat forever. And you can control the animation's curve. So what do we mean by animation curve? Well, the animation is happening over time, right? Maybe it takes 1 second or half a second or 2 seconds even to do an animation. And how fast does it go from where it's starting to where it ends? So if we got scary on the previous slide, the switching, and it's going to go from fully transparent to fully opaque, how fast does it go from one to the other? Or if we're going upside down, how fast does it rotate around? Well, if it has a linear curve, it's going to rotate or fade in a linear fashion. Basically, consistent rate is going to be the same speed of change all the way through it. But a much more common kind of animation is easing. So there's ease in, there's another one called ease out, and then there's this one, ease in out. And what easing means is, for example, ease in out here is it starts the animation off a little bit slow and then speeds it up and then slows it back down towards the end. Make it a little smoother and calmer at the beginning and the end. And it's very common. This is actually the default animation to do that. And then a spring animation curve is it just starts animating normally, but when it gets to its destination, like especially when we're moving things on screen, we use springs, it gets there, it kind of overshoots its mark maybe a little farther than it was supposed to go, and then kind of springs back a little bit and oscillates at the end. And this provides a little bit of a more natural landing motion for things that are moving, although you could use spring on other kinds of animations besides moving, but it's easiest to imagine for that. So these curves are essentially saying the timing of how fast the animation goes through its duration. It's not the total duration, that's a different thing. It's more like the speed at which it's going through the duration. These implicit animations, these automatic animations where you put dot animation there, they're usually not the primary source of animation behavior. They're mostly used on leaf, Lego brick type of views because of the weirdness where it gets kind of distributed through a container. Maybe more generally, they're used on views that are kind of independent of all other views, views that want to do their little animations no matter what else is going on. A lot of times we'll use them on controls, little switches that we want to give a little feedback when you press on them, things like that. It's not really the primary way that animation happens in your app. A more likely cause of animations happening is some change to your model, or the user clicks on something that causes the UI to rearrange itself in some way. For these kind of changes, reacting especially to user input, we're going to use explicit animation, which is a different way of doing animation. So explicit animations create an animation transaction during which all eligible changes to view modifiers and shapes get animated together using whatever animation curve you specify. And it's really simple to kick off an explicit animation. You just use this simple Swift function with animation. It takes the animation that you want, right? Which curve and duration, etc. And you do something in a block. And when you do something in that block, it's going to animate all the view modifiers that changed because of what you did in there. For example, explicit animations are almost always wrapped around ViewModel intent functions. Because a ViewModel intent function is very likely to change the model, which is going to change the UI, and we want to animate those changes. But it might be wrapped around things like enter edit mode, which is just going to change some things on screen to go into an editing mode or whatever, have some extra switches it didn't usually have. It's fairly rare actually for code that handles some sort of user gesture, a tap or something like that, to not have a with animation wrapped around it, because usually we want to respond to things our user asks us to do smoothly, and that's what animation is all about. Explicit animations like this, calling with animation wrapped around something, they do not override implicit animations. The little dot animation view modifier that you add, this does not override that. those little dot animation implicit ones, they're assumed to, again, be kind of independent of other animations. And so they're not going to be affected by an explicit animation. The last one we're going to talk about is transitions. This is the comings and goings of views. Now, again, this is at least the third time I've said this. This only works for views that are inside what I call CTAAOS. I tried to come up with a good acronym for this, but I just couldn't, so I just went for this wacky one, and I'm emphasizing here in blue. A CTAAOS is a container that is already on screen, right? That is the only kind of coming and going of a view that gets animated. Now, under the covers, the transitions really are actually view modifier arguments changing. We're not going to talk about this, but essentially a transition of a view coming on screen or going off screen is just a view modifier for what it looks like before it comes on screen, and then another view modifier for what it looks like after, and then just animating the difference between the two. So that's really all that's going on there. And it is possible to have what are called asymmetric transitions, where a view fades in on screen, but then it flies off when it leaves the screen. That is certainly allowed. Mostly when we're doing transitions, we're going to use pre-canned ones provided by the system, like fading in and out and scaling in and out and moving across the screen. And these are all provided via static vars and funcs on a struct called anyTransition. Now, transitions are type erased. And we're not really going to talk about type erasing right now. I might talk about it a little later in the quarter, but the idea behind type erasing is, for example, in a transition, I told you underneath it's a couple of view modifiers that are modifying changes in views, and that'd be a lot of types in there. So if you really had the full type of such a transition, it would be unwieldy to work with, and we don't actually care. All we care is this fades the view out, or this moves the view, onto screen, or whatever. Any transition, it has that any in the front because it's type erased transition there, and so thus it is any transition. We don't know which, and we don't care. What do these pre-canned things on any transition look like that we use? Well, there's opacity. That uses the opacity view modifier to fade the view in and out. That's the default, by the way. There's scale. Scale uses the frame view modifier to make, if it's appearing, it goes from a tiny infinitesimally small dot, whoop, and it grows up to expand to its normal size on screen. Or when it's disappearing, it shrinks down to a tiny infinitesimally small dot. Offset, you can have the view move from maybe somewhere off screen and fly on screen, or move from somewhere else on screen. And you can even provide your own view modifiers for the before and after. I'm not going to talk about that, but I don't want you to get the idea that any transition only can do these pre-canned ones. You can build your own if you're really good at building your own view modifiers and such. How do we specify which of these things, opacity or moving or whatever, that we want on a view when it comes and goes? Well, let's look at an example of this. I have the Z-stack here that looks kind of like a scaled down version of our memorized cards right there. Right? It's got an is face up with one rounded rectangle there and some text, and then it's got another rounded rectangle. The one at the bottom is if it's the back. So this is a little lighter weight version of the one we have. And so let's see what we got here. We've made the rounded rectangle that's on the front, the first rounded rectangle there. It has no dot transition specified on it. So this dot transition modifier that we put on this, we're going to put it on the ghost one there. It says when this view comes and goes, use scaling. So make it go, to a tiny dot and reappear from a tiny dot. And the back rounded rectangle, it has a dot transition declared on it, which is dot identity. Now, identity means use the same version of me before and after. So this means really no animation. When I come and go, just make me pop on screen, just appear. So don't use anything but my identity. I'm going to look exactly the same before and after a transition. I put transitions on only 2 of these 3 views. So as long as this Z-stack is on screen and we're in the middle of an explicit animation, so we did with animation, let's say that if phase up changed from false to true, so the back was showing and now we're going to show the front. Well, the back would instantly disappear because it's got the identity transition. And then in the front, the rounded rectangle, stroked around the edge, it would fade in because it's going to use opacity, which is the default transition. And at the same time it's fading in, the text is going to scale in from infinitesimally small up to the normal size of the text. So that's the kind of animation would happen when these three views kind of swap in and out from being in the UI. And they're swapped in and out because there's that if that's in this view builder of the Z stack. So ifs in view builder is the primary way we swap views in and out. Now, unlike dot animation, this dot transition does not get propagated in. So if I put dot transition on the Z stack itself, now I'd be talking about the whole Z stack. How does it come and go? And so all the views inside of it would all fade in together if the Z stack had an opacity transition. So it's very different here specifying dot transition versus that implicit animation thing. The implicit animation would put the implicit animation on every single view separately, whereas dot transition means the whole thing. In other words, dot transition is more like dot padding, applies to the actual container, and dot animation is more like dot font, dot foreground color, etc. Now, group, which we're going to talk about in the demo, probably next demo, and for each, which are really bag of Lego kind of view containers, they do distribute their dot transition in. And that's generally true of bag of Lego type of view containers. They really transmit everything you send to them into their views. But Z stacks and lazy V stacks and all that, when you say dot transition on them, you mean the entire thing, the entire lazy V stack. You don't mean each view inside. This dot transition modifier, by the way, think of it as a noun. You are saying this is the transition to use. You're not saying, please transition this view right now. In other words, don't use the word transition as a verb there. It is the transition to use. Scaling, opacity, moving, which transition do you want to use when this gets animated? Because it's usually going to be animated by an explicit animation. Now, it is possible actually to set an animation on a transition. And that is going to set the curve and duration and such to use just for this transition. It got the same name, dot animation, as the implicit view modifier does, but we're not using it as a view modifier here. I'm actually using it on the transition. Notice the green code there, any transition dot opacity dot animation. That is setting the animation for this opacity transition that I'm declaring for some view. All right, the comings and goings of views. There's one other way you can specify the animation of the comings and goings of views, and it has to do with when views are moving around. Now, normally when a view moves around, it's moving in the same container view. So I have a lazy V grid and it's got a bunch of things in there, and maybe I've got a for each that says what all the views are, and that for each gets shuffled or reordered and all the views move around. Okay, that is normal animation. It's in fact just animating the position view modifier that lazy V grid is using to position all of its views. Nothing special about that, nothing to see here. There's no transitions, no views are coming and going there necessarily. They're just moving around to new positions. And if you explicitly animate that, they'll move smoothly from place to place. But what if the view that you want to move across the screen is not in that lazy V grid, it's somewhere else? Okay, this is not really allowed. Okay, you're not allowed to have views. How would you even declare that in SwiftUI? It's impossible, you can't do it. So how do you make this work if you wanted a view to appear to the user to move from one container over to another container? Well, what you have to do is put a view in each of the two containers, and then you can match their geometries, and I'm going to show you how to do that. And once you match their geometries, then you just make sure only one of the two is ever included at a time, and as one appears and the other disappears, the one that's appearing will match its geometry to the one that's disappearing, and then it will animate both its size and position to fly over to where the new one is appearing. So it's a view transition thing, but it's when you have a pair of views, one's always disappearing at the same time the other one's appearing, and they kind of mean the same thing to the user. A great example of this is if in our memorize game, instead of just our cards appearing, what if we had a little deck of cards in the corner of the screen, and then we just dealed out the cards, deal like a normal dealer would deal the cards. Well, if we did this, the views would kind of fly from the little deck over to our lazy V grid, but those would not be the same containers, and so we would need to match up their geometries. And we do this really simply by just putting the view modifier match geometry effect on both of the views, both in our lazy V grid and in our deck. And we just want to make sure it's never showing in the deck at the same time it's showing in the lazy V grid and vice versa. And this match geometry effect takes two arguments. The first one is an ID. This just identifies the view. So in our card game, it would be probably the identifier for our cards. Okay, that ID can be any type. It just has to be something hashable. And then it also has a second argument, namespace. Well, namespace is just a token, and you create this token by saying @ namespace private var my namespace. You put that in your view, and it just keeps the namespace of that ID separated in case you have maybe two completely different geometry effects going on, and they're both using integers as their IDs, and you don't want them to conflict. So that's all the namespace argument there is. You don't have to do any more than that second line in green up there. Now, got this marked on both views. Now you just write your code so that they never appear on screen at the same time. And when one appears and the other one disappears, they'll fly over to the other one. It's as simple as that. We're going to do this in the demo. You'll see exactly how this works. Pretty cool effect. All right, another thing to talk about. Remember that fifth time I told you, animations only work in views that are in containers that are already on screen. Well, I'd like to find out when my container comes on screen, and then I can do some code to make the children inside then come on screen after. And that's what onAppear is all about. So onAppear executes a closure when a view appears on screen. You use onAppear on a container view, and when that container view appears on screen, you get to execute some code. And since by definition, that container view is now on screen, otherwise onAppear wouldn't be happening. All the views inside are now in a container that's already on screen. And so if you change something about them, maybe change your model at that point, or change some @ state vars in your views that affect whether those views appear, they can now transition to appear on screen. Or maybe you're going to change some of their view modifier arguments and they're going to rotate upside down or something like that. We're going to use onAppear a couple of times in our demo. One time we're going to make our cards auto deal when our UI first comes on screen. As soon as it's up and appears, then we're going to automatically deal the cards out using animation. And then also our pie, the little pie on our cards that keeps time, keeps track of how much bonus time we've used. As it counts down, every time the pie appears, it's going to start itself animating, which is a common thing to want to do with onAppear as well. We talked about how to kind of kick off animations and make them go and describe what transitions to use when views come and go, all that stuff. But how do animations actually happen? Okay, we know these view modifiers, like these geometry effect things, position and rotation effect, all these things can do it, but how do they do it? Well, the animation system is essentially taking that duration that the animation is happening over, and they're dividing it up into little pieces depending on what the curve is, right? So the pieces might be a little smaller at the beginning, then a little bigger in the middle, and depending if it's ease in, ease out, or the spring. You see what I'm saying? It's chopping it up into little pieces. And then the shape or the view modifier lets the system know what information inside it needs to be animated. For example, the pie wants its two angles, the start angle and the end angle, to be animated. So it has to let the animation system know, yeah, please animate the start angle and end angle for me. And we'll show you how that works. And then during animation, the animation system just calls them back and says, okay, please draw yourself with this start angle and end angle. And then it goes to the next little piece and it asks it again. Okay, now draw yourself with this start angle and this end angle. It just does that repeatedly. So maybe the start angle starting at 0, and then it goes to 7, and then it goes 12 and 23, 31, 45. It's just moving the start angle and repeatedly asking the shape to redraw itself. Same thing with the view modifier. It's saying regenerate your body's content with this animated value of your piece of information. How do shaped and view modifiers communicate with the animation system? Through this one var, okay, animatable data. View modifiers that are animatable, they're called animatable modifiers. They implement the animatable protocol, which has this var in it. Shapes always implement the animatable protocol, so they have this var in it. And this var has a certain type. This type is a don't care. Well, care a little bit. This type has to implement the protocol vector arithmetic. And you can kind of tell by the name of it that you need this because whatever this animatable data is, it's the thing that the animation system is going to chop up into little pieces and hand back to the shape or the view modifier through the whole animation process. Now, this type is very often a floating point number, like a double or a CG float, but it could be something called an animatable pair. So an animatable pair is itself a vector arithmetic that just combines two other vector arithmetics. So now you could have two things. For example, in our pie, we want to animate both our start angle and our end angle. So we will be using an animatable pair as our animatable data, and the animatable pair will have the two angles in it. Now this var animatable data, it is actually communicating both directions between the animation system and the shape or view modifier. The setting of this var is just the animation system saying, okay, here's the next little piece, you draw this. Here's the next little piece, draw this. So that's how the animation system tells it to draw. But the getting of the var matters too, because when you set a view modifier's argument, for example, that's going to change that animatable data probably. So the animation system can get the value of this var to find the start point and the end point of the animation it's supposed to do, right? The start point was the value of that animatable data before the argument to the view modifier changed, and then the end point is after it changed. Now, usually this animatable data is a computed var. It doesn't have to be, but the reason it usually is our code inside of our shape or view modifier doesn't really want to have the variable animatable data be in there. It wants to use names like start angle and end angle that are more meaningful to what it's actually doing. So a lot of times we'll make this computed var that just returns the start angle and end angle. And when you set it, it sets the start angle and the end angle. We'll see that. We'll do that for both our pie shape and our Cardify view modifier. We're going to animate our Cardify view modifier so that the card actually flips over. It doesn't just fade in and out or something like that. It looks like it's in 3D flipping over in front of the user. And speaking of that, let's get to the demos. This animation is probably the largest demo we do all quarter. And so I'm going to start it today. I'm going to talk about implicit animation at first and a little bit how to diagnose when we see something that we thought was going to be animating and it's not, and how do we find out what's going on. But then I'm going to continue with the entire next lecture. It's going to be as much animation as I can fit in there, every different kind of thing you can imagine. So that is going to be a huge demo-only lecture. That'd be lecture 8, I guess. But let's get our first taste of animation here with implicit animation. Implicit animation is an animation mechanism where every single time some arguments to some view modifier or modifiers change, you want to make sure that gets animated. This is quite different than explicit animation where some action is happening and you want to make sure that that entire action has a response in the UI that gets animated. Implicit animation is much more rare, and you have to sometimes be careful that your implicit animations don't interfere with your explicit animations, which are the primary way you're going to be doing animation. Now let's take a look at an implicit animation that might make some sense. So I'm going to do a lot of the animation demonstrations in the simulator here because the preview window, while most things work there animation-wise, not all of them. So the animation I want to do here is when I click two cards that match, I want these little emojis right here to spin around. And they're just going to really give you the joy of matching here by having those things spin. Making things spin around is a geometry effect. And you're going to find a lot of animation as geometry effects, whether it's moving things around, resizing things, scaling things, in this case, rotating things. It turns out to be quite simple to rotate things. We're going to rotate these emojis, so that's just this text right here. I'm going to put a view modifier on here called rotation effect. And you can see the rotation effect takes some arguments here, like what axis you want to rotate around. But it also has a simple version that just takes the angle and it rotates around the center of the view. So I'm going to do this. We create an angle. Of course, we already know how to do angles from our work with shapes. I'm going to specify it in degrees. And if the card is matched, then I want it to be 360 degrees versus 0 if it's not matched. This ternary expression right here, where you have some Boolean and then a question mark, and then what if it's true, it's this, and if it's false, it's this. You see this an awful lot with view modifiers. And the reason for that is that the only time that view modifiers can be animated is when they change. So if the arguments to a view modifier are not changing, then no animation can happen. And that is one of the primary rules of animation we talked about in the slides. Animations animate changes, so things have to be changing. So here, this number of degrees is going to change when card is matched, because if it's not matched, then it's going to be 0, and as soon as it gets matched, now it's going to change to 360, and so this becomes animatable. Now, if I run this as is without any animation, it's going to look like it does nothing. Click on a card, I got a match. I didn't rotate, I don't see any rotation effect. Well, in fact, it did rotate it all the way around 360 degrees, but since no animation was happening, it happened in an instant. And that really is another of the laws of animation, which is that animations are showing you things that have already happened. It's just showing them to you all over time. So when I do this rotation effect here and the card gets matched, it immediately has gone around 360. But if I put an animation in, then I get to see it happening more slowly on screen than it actually happened in real life. So how do I turn on this animation? Again, the number one way is it would be explicitly animated, because I'm going to animate, for example, the action of turning cards over or something like that. But here we're going to do an implicit animation just to show you. Now, putting an implicit animation on this effect is going to cause it to do this rotation when the cards match, no matter what the context is. And it is possible to override these implicit animations and turn them off, but it's not straightforward. It involves an API I'm not even going to talk to you about called transactions. But you know, as long as you're comfortable with this rotation effect always happening, always being animated, then we can put an implicit animation, which is just animation, and we provide the animation. Now I'm going to create an animation here. If you say animation dot, they're all, as you can see, static functions or static vars. So we put the type animation here and then dot, and then we're going to pick these. Again, remember, static functions are just namespaced functions or vars. And we're usually going to choose from this predefined set here. Notice a lot of them start with the word ease. Ease in, ease out, with duration. And this easing is that you don't always want an animation to just start going and then stop. Sometimes you want to ease into it and then speed up a little bit and then kind of slow down at the end. And that's what this easing in or easing out is all about. And of course, the duration is how long it's going to take for the animation to happen. And most animations, you're not going to specify the duration. You're going to let the system choose, and it chooses pretty good times usually. You also see that there's a bunch of them that are springs, these interactive spring, interpolating spring. A spring animation is one where the animation kind of goes to the end point of whatever you're animating, and then it overshoots a little. And then it kind of springs back, and then maybe a couple of little oscillations before it gets there. And so especially for movement, obviously when things are moving across the screen, spring animations can be good, but other kinds of animations as well. Then there's linear. Linear is probably what you thought animations do. They just start up and then they do what they're going to do and they stop and they're just going in linear time. But linear is not necessarily even a common animation. These ease in, ease out are much more common. You can also see that there's some things here with repeating. We'll look at these in a moment. This timing curve right here, you can specify your own curve of how the animation progresses over time. Although we rarely do this, we're usually going to want these pre-canned ones because, again, that's what other apps are doing. Users are used to these kinds of animations happening on these timing curves right here. We're going to choose ease in, ease out here because that is the default animation. And I am going to give it a duration just to slow it down a little bit so you can see what's happening. So let's go with a duration of 2. Now let's run and see what this exact same rotation effect looks like, but when it's animated here. And you can see it rotated around. It took 2 seconds. I don't know if you could notice the ease in and ease out of it. See, it kind of slows down at the end, and when it first happens, it's going kind of slow. So that's what the ease in, ease out feels like. Now I can see right away that there's a problem here where only one of the 2 cards is doing the spin. We're going to figure out why that is in a second. But there's another subtle problem here too. If I rotate my device, I get some pretty wacky results right here. And so we're going to look into that as well. But before I do that, I want to do one other simple thing, which is that it spins once. What if I wanted just to keep spinning around? Well, you can have your animation just do it once, or you can tell it to repeat, either repeat a certain count or just repeat forever. If we say repeat forever, let's take a look at what that looks like. This goes around and it just keeps going. Now, look, it went around once and then it kind of backed up and then it repeated. So I don't really want that. I kind of want it to just keep going around and around and around and around without this reversing. You can do that here with auto reverses false, or it does not auto reverse. And the default is obviously for it to auto reverse. Now, see how it's doing the ease in and ease out each time around? Maybe I don't want that. Maybe I want this to spin in a constant linear motion. Well, then I would choose a linear animation. And that's probably too slow. We slowed it down so we could see what's going on. Probably going to want either standard duration. Let's see what the standard duration animation looks like. That's a little too fast. It's going so fast I can't even tell that it's a bike anymore. And some of the reason for that is, the standard animation is pretty quick, and this has to go all the way around. So I'm thinking that a duration of maybe 1 second might be a good duration to give us the feedback, be excited about our match, but not too fast or not too slow. So why is this problem happening where we're getting this really junked up animation right here, especially once we start to repeat forever, everything seems to be having a problem. This actually has to do with the fact that we're putting an animation onto something that's not really animatable. This text right here is not animatable primarily because it has a font right here, font modifier, that is varying the size of the font. And font is a view modifier that is not animatable. Changes to this do not get animated from one state to another. We have this being animated, and especially when we do a rotation, now we have multiple animations going on at once because these cards slightly change size when you animate, and of course they're changing position. Plus we've got our little spinning, rotating thing. So this is not looking good. We clearly need to somehow fix this. And the only way to fix this is really to have this thing animatable. Having it animatable means we can't use this way of setting fonts, but there are other ways to scale our font up to fit what's on the card. For example, I could pick a fixed size font, say 32 or something, and then use a scale effect. So scale effect takes some scale, and this can either be a number like twice as big or half as big, or it can even be a CG size, which means you could scale it differently in the width and height. And we could pick a scale for this that has this font ending up being the right size based on the geometry. So let's create a little function to do that. I'm going to have a function called scale that fits my geometry's size. Private func scale that fits size, CG size, return some CG float scale. And I'm just going to take the min of our size.width and size.height, the same thing I did when we were trying to pick a font that fit this way. And I'm going to divide it by some constant that relates the geometry size to the scaling that we want to do to make our text fit. So to do that, I'm going to turn this 32 into a constant, drawing constants. I'll call that my font size. Let's go down here and create a static let font size, CG float, make that equal to 32. I'm going to take this drawing constant font size and divide it by our existing drawing constant font scale to try and get pretty much the same effect we had down here. We don't need this anymore, we're not doing that. So this is a different way of working. Now, the reason this works is now we're picking a fixed font. We are not varying the font, so this font does not have to animate. The scale effect does animate, just like rotation effect. This is a geometry effect. All of these know how to animate. Let's take a look at that. All right, so it looks like the bike, it might be slightly bigger, but it's pretty much the right size. And let's hope that when we rotate, well, now, since the card can size to this new size and position and animate all the pieces, you don't get this kind of jerking around, jumpy effect. Notice, by the way, that this animation that we added right here to cause this rotating train did not affect the scaling. We do the scaling and font effect. It wasn't repeating forever every time we rotated the device and caused the scaling to change. And that's because this animation view modifier is modifying this view and only this view. Animation modifiers apply exactly to the view that you applied them to. So if you put this animation modifier lower down here, then it would affect these things. So placement of animation modifiers is very important. And of course, we also learned in lecture that putting an animation modifier on a Z-stack is kind of like foreground color. It's going to apply that animation to every view inside the Z-stack, which is one of the reasons we rarely put implicit animation modifiers like this on combiner views, because often doesn't make sense to apply them. And of course, it's going to apply them to the bottom of every single view inside of it right there. And that can give very undesirable results. So these animation view modifiers are usually for Lego bricks, not dining room chair Legos. And you're going to want to tuck them right up against the things that you really want them to animate, unless you really want all these things animated. So placement of these is quite important. All right, our last thing to fix here with this implicit animation is the fact that it doesn't even work on this card. Why is this animation just not happening on this card? It's clearly working, but not on this card. Well, when you have an animation like this and you expect it to be working and it's not, you probably want to go back to the golden rules of animation. One of them we know is that animation only animates changes. And so what change is happening that causes this rotation effect to go into effect? It's this card matched change. Card is matched changes. That changes the argument to this rotation effect. That's a change, and this animates that change. So is card is matched changing for this card? Well, it definitely is because it was face down and I touched on it and it flipped face up and matched. So it changed to be matched. When it was face down, it wasn't matched. So now that it went face up, it matched. So that is not the problem. So let's go to another golden rule of animation, which is we can only animate view modifiers for views that are already on screen. Views that are coming on screen, and also ones that go off screen, those get animated in a different way. That's the dot transition modifier that we talked about before. So this is not that. This is an implicit animation. So it's only animating view modifier arguments. So let's make sure that this view, this text, is on screen at the time that this change happens. So when does this text come on screen? Well, let's trace it. This text is in this Z stack. So whenever this Z stack comes on screen, this text is going to come on screen with it. When does this Z stack come on screen? Well, let's get Cardify. Let's go look inside Cardify. Inside Cardify, this Z stack is called content right here. So where is that? It's right here. When does this view come on screen? Oh, it comes on screen when is face up goes to be true. So anytime is face up becomes true, boom, this comes on screen. And actually, if is face up goes back to false, then this goes off screen. This view, this little text that's inside that Z stack, it's coming on and off screen quite a bit as these cards go face up and face down. When this goes face up in this matching case, what is the state of card is matched? Well, it is matched because when you touch on this card and it goes face up, it tries to match, it is matched, it goes is face up and is matched at the same time. So it's coming on screen with is matched already true. If we go back to here, this is matched true means that it comes on screen with a rotation effect of 360. In other words, it's already rotated. So there's no change to animate. It came on screen already matched. The is matched didn't change. It was true from the start for this card. That can be a subtle thing to understand and track down is when your views come on and off screen and what the state of the model is at the time. So how are we going to fix this? Well, we need to fix this by making sure that this text is on screen when this matched happens. But if this text only is on screen when is face up happens, we got a problem because those happen simultaneously, is face up and is matched. So why don't we just take this content and take it out of there? Just make it so that the emoji text, that Z stack with the emoji text in it, is on screen all the time. Well, I suspect this is going to solve the problem. Since it's on the screen all the time, then of course it was on screen or it'll be on screen when is matched happens. But this doesn't look too good because now the emoji's on screen when it's face down, right? It's no longer inside here. So yeah, it's on screen when it's face up, but it's also on screen when it's face down. But let's at least see if this fixes the problem because now it's on screen all the time, face up or face down. There we go, and oh, look, fixed the problem perfectly. They're both animating. So here we used the golden rule to fix this problem, but kind of put us in a pickle because we now have these terrible looking face down cards where we can see. It makes the game really easy, but it's not exactly what we want here. How are we going to make this not show this text when it's face down if I can't put it inside this if then? Well, there are other ways to make it so that the user can't see a view, then taking it out and putting it back in whenever is face up changes. We already know one of them, in fact, which is dot opacity, right? Opacity makes it fully transparent or fully visible. So why don't we just say that when it's face up, the opacity is 1, fully visible, and when it's face down, it's 0, completely transparent. So it'll be there, it's just the user is seeing right through it to the back of the card. So from the user's perspective, it's not there. This is kind of a good trick. If you have some animation you want to happen on a view and you can't have it coming and going like this, you know, being included and then not being included as variables change. See if that did the trick. Well, it certainly seems to have hidden the emoji in the face down case. Let's flip some cards. Oh, there it is. It appeared. And how about here? Oh, it appeared and they both animated because this was always on screen. Even though it was transparent, we couldn't see it when it was face down. It was still there, just kind of hiding. And so when is matched happened, it was on screen. And so this is matched change right here got animated by our implicit animation. So that's all I really wanted to show you with implicit animation. I'm not really going to do any more examples of that. Again, it's pretty rare, and we have an awful lot of other animation to cover, which we will continue doing in our next lecture.
For more, please visit us at stanford.edu.